Hello. Thank you
Hello.
so much for inviting us. Just a bit of introduction while I share my screen. I'm Kimberly. I'm the president of Texas Guadaloop, and we're a Hyperloop organization on campus at the University of Texas at Austin. Currently, we have so many projects going on. We're planning on participating in European Hyperloop Week, and also CHC in Canada. So we have a lot of projects to show. Don't want to take too much of their time just introducing us, but you can follow us on Instagram, LinkedIn, and other social media platforms. But I'll take it to active guidance to talk a little bit about them. Here, you can present.
So are you guys able to see the screen right now?
Yes, we can.
Okay, sounds good. So active guidance is our subsystem that will be used to levitate the pod. And we're doing that using EMS. And I'm not sure if you guys can see my cursor, but the bottom right image is our yoke, and it's in the geometry of an E. And we will have coils around the middle beam of that E in order to reduce the magnetic flux of the yoke. And there's going to be two permanent magnets on the left column and the very right column of the E yoke. And without any current running through the middle coil, the yoke will actually have enough force so that it will just stick up to the track. So in order for the pod to not stick to the track, we will be running current through the middle beam of the yoke to reduce the flux of it. And we will have optical laser distance sensors in order to have the feedback control of how much current we should supply to the coil. And the reason that we have it in an E geometry is so that we do not demagnetize the permanent magnets on the yoke.
Hi, so this is braking system. So we have two main braking systems on our pod. We have a pneumatic braking system and we have a regenerative braking system. And so the pneumatic one is used for emergency case scenarios, in case the limb doesn't stop or we run into just worst case scenarios. That one we're using a pneumatic brake caliper, and we're attaching that to the brake disc on bearing load wheels, and that will stop it within reasonable enough time. We also have a regen braking system. There will be two of those wheels in the middle of the pod. We're using 24-volt DC gearless hub motor wheel with a rated efficiency of 84%. And that, after running calculations, we will be able to, because we have a limited track length, we'll only be producing 22 watts for our pod. But whenever we run it at 80 kilometers an hour for a mile making contact, we're producing around 10,000 volts. So that's our braking system. It works in most case scenarios, or in all case scenarios. The regen is for everything except for emergency, pneumatics for emergency. This is comms.
Yeah, so comms communications is a system that we have that is responsible for the communication with the pod or the vehicle, and also for gathering data from the sensors on the vehicle. And we have currently tested and designed a one-way communication for communicating with the pod, and we're currently working on a two-way communication, which is sending data to the pod and from the pod with the long-range radio communication. We also have done logging, error detection, encryption, and we have a dashboard server where we will be hosting and storing all the information. And we're designing this such that it is scalable and we can add more what we call meshes to the network, so we can expand more upon the communication and make it more scalable in the future. And for embedded systems, we have, as you can see here in the right, a a architecture based on a real-time operating system. And this allows us to have efficient task management, which is easier for us to program and also have real-time response to safety critical events. And we are using a canvas for communication between all the devices that we have placed throughout the vehicle. It's industry standard. It's very robust against interference, and it gives us quick response to events such as gathering sensor data for braking, emergency braking, or for propulsion of our pod. And it's also very scalable due to its network topology, allowing us to just add more devices as we need. And we also have a vast sensor suite. As we can see here in the diagram, we have a lot of sensors for a lot of different things, such as telemetry, safety control for emergency braking, and some feedback control as well for active guidance.
So this is the frame of our system. We're using aluminum 61 T6 as the main material. This is a non-ferromagnetic material that will not interfere with any of our sensors. And within the frame, we're going to have some insulation, like similar to like the insulation you'd see in your drywall, to make sure that the electronic systems of our pod are not interfered with in any case within the active guidance yokes or the limb. And the frame will overall just house all the electronics and mechanic systems. It will be bolted to our shell of the pod outside of the frame using a 1/2-inch hex bolts. And this will mount within the track and have a gap on each side of about 90 millimeters, which accounts for the extension of both the limb and then the necessary gap that we need between the limb and the track to operate in the optimal conditions. And then our projected dimensions currently are about 6 feet long by 18 inches tall and 40 inches wide. And this is what we determined as the best geometry after we set up our FEAs to ensure an FOS of above 2, including for all the magnetic forces from the yokes and the weight of things like the HV battery and the LV battery and all the electronics of the subsystems. Then I'll kick it off to Ibrahim for manufacturing.
So in terms of manufacturing, we're preparing the club, the Texas Guadaloop to the manufacturing season. We're creating the GHAs and the SOPs for hot work, metal work, composites, and any other manufacturing methods that we're going to do. We're also working on a project for our, we're working on a proof of concept for our vacuum chamber. We have another project called Operation Restore Pickle, which is we're restoring our facilities. We're getting new tools and installing so that we're completely ready to go when the manufacturing season comes. Also, we're doing workshops for manufacturing processes, such as welding, hands-on workshops for welding, composites, and metalwork. And I'll kick it off to power electronics.
Yeah, so for power electronics, we have 3 main components. We have the low voltage system, which is responsible for powering all electronics, such as like sensors and embedded systems, some of the braking, regenerative braking components, and anything that requires a low voltage and low amperage. And then we have the high voltage system, which is responsible for supplying voltage to the limb, which is the linear induction motors, and the active guidance system. And these systems require a lot of voltage and amperage, which is why we have split it into low voltage and high voltage systems. And the last component is the inverter, which is responsible for controlling and powering the linear induction motors. And this inverter has canvas capability. So as I mentioned previously, we can just easily add that component to our canvas network and have the embedded systems control it and interface with it. And it is, again, like I mentioned, for controlling the limbs. So now I'm gonna pass it on to propulsion.
So we will be propelling the pod using a linear induction motor. It is contactless and it uses 3-phase AC in order to create the propulsion on a conducting material. And the conducting material that we'll be using is aluminum for the track. And the core of the linear induction motor is made out of 280 laminated electronic steel, and it's 0.25 millimeters thick each. There are 8 coils per phase, and it will be mounted on the frame. And the other half of propulsion is the power electronics that will be powering the limb. And we'll be using a 400 volt, 120 amp DC power supply connected to the Balmacar D3 inverter, which will invert the DC supply to a 3-phase AC. The power electronics also has a pre-charge and discharge circuit so that we do not damage the DC link capacitor within the Balmacar. And the discharge is for safety in case power is lost so that we could discharge the capacitor within the inverter.
And then this is the shell of the system. So I'll just be talking about the design, testing, and manufacturing. So these are a couple of the initial designs we had, and our shell is up at a high level, supposed to house the pod and all its components in an aerodynamic and efficient manner. So right now we're working in CFD testing to minimize drag as much as possible, and we're using SolidWorks to do these tests, and we're just continuously redesigning based off these CFDs, trying to minimize the wake region as much as possible and limit the drag coefficient to minimal values. And then once we start testing, we're going to 3D print our shell models and put it in a wind tunnel and test for things like the Reynolds number, the drag coefficients, and see if our model holds accurate when we scale it up to the real world. And for our manufacturing process, we're going to be manufacturing the shell out of fiberglass because it's cheap and it has the structural properties necessary to support the shell in like fail-safe scenarios, which we hopefully expect should not happen. But at the very least, it can support the static weights that would be held within the shell. And we're going to be manufacturing this in-house using MDF tempered hardboard to create our molds and then creating foam within that and then doing the layup process from there. And when we do this, we're going to dry cure it, and that should give us the properties that we want. And I'll kick it off to suspension.
So these are suspension mounts. Suspension and braking are very integrated. The braking wheels would be attached to the suspension mounts. And so we'll be using that not only as barriers and keeping the pod safe and dampening the forces that we'll feel from the electromagnetic, the yoke and the active and the limb, but it'll also act as a barrier and braking. And so what we have here, that top picture is our lateral suspension mount. We'll have 2 on each side, and those will just act as a barrier with a 4 millimeter gap so that it doesn't make contact with the track and cause damage to either the track or the pod. And so right now at forces of 1,000 newtons, we're seeing an FOS of 9. So we're really seeing good structural integrity for this lateral suspension mount. And then for our vertical mounts that will house our pneumatic and regen braking systems, we're expecting a force of about 1,500 newtons, and we're seeing an FOS of 15. And so to make these will be mainly made out of aluminum 6061 T6, and we're going to be welding these individual parts together. We're going to be making all these mounts in-house with metal sawmills. And so, we chose aluminum so that it wouldn't affect with the electromagnetic waves from the limb and our levitation system. Now I'll pass it off the track.
Hello, this is going to be our track that we'll be using. In previous years, we've used I-beams, but this year we decided to create a custom track with an overhanging design because it'll allow for our magnetic levitation to counteract the weight of the pod. So less external forces to be on the track. You can imagine our pod being completely underneath, and all of our systems are going to be interfacing with this L flange, and all of these other supports are just going to be there for structural integrity. So we have a steel-backed aluminum flange. The steel is, we want to use the steel because it's a ferromagnetic material, and we need that for our magnetic levitation. And we have the aluminum because it'll create eddy currents for propulsion. We went with this design also because it's modular, so this would be one segment, and we would be able to add on more segments if we wanted a longer track. And so far we've been running static FEAs, and they show that we have a factor of safety of 28, so we're confident that it will be able to withstand all of our forces in emergency situations.
Yeah, so that pretty much wraps up a little bit about what we're doing right now. Of course, there's a lot of work in progress, but I'm just opening the floor to any questions y'all have for us. Thank you.
Thanks, guys. Very cool to hear from you. Any questions from anybody? Raise your hand or type in the chat.
Okay, we're good. Thank you guys for inviting us. It was so good.
Of course. Hopefully we get to see you in person this year too.
For sure.
Yes, excited. Very cool.